Good morning, pandas. This is Mr. Stam. Hope you're enjoying your was supposed to be opening day for the Cincinnati Reds. Obviously, in a situation we're in, that's not happening. Got wear your red stuff today. Maybe go outside, toss the baseball around. That's what we should all be doing probably. But today we're going to continue yesterday's discussion on how to draw Lewis dot structures. And Lewis dot structures, sometimes doing the method we did, when you're counting up your dots that you drew around your structure and you're seeing how many valence electrons you should have, sometimes they don't equal each other, which means your structure is wrong. Well, what happens if that's the case? Well, if we're continuing our presentation here, the first thing I would check would be that there are double or triple bonds in the structure then. You have to draw a double or triple bond, which I'm going to show you how to do today. Or possibly, this is more maybe talking about tomorrow, the structure is legally violating the octet rule. So it's not following the octet rule like we would expect it to. And some elements can do that. We'll save that one for tomorrow a little bit. So today we're going to talk about the double or triple bonds in the structure. So how do we make a double or triple bond on our structure? Or how do we know we have to? If a molecule's dot total is greater than the number of valence electrons, so the number of dots that you drew following all of our rules is greater than the number of valence electrons that you calculated looking at the formula, it has either double or triple bonds for the most part. And you always start looking for double first and then possibly triple. The only atoms that can form double bonds, though, and this is kind of a key thing because you can't make a double bond on certain elements, so you don't even try to do that. The double bonds can usually only form around carbons, oxygens, sulfurs, nitrogens, those kind of elements. So carbon, oxygen, sulfur, nitrogen, those are the ones you want to look at. Really, for triple bonds, the only things that can do it are carbon and nitrogen, and sometimes oxygen, but we're probably not going to see that. So carbon and nitrogen are the key points here. So the reason for this is it's a matter of size. It has to be a smaller atom for the bonding to be able to occur. So that's the reason why I'm really concerned about that. The double bonds, carbon, oxygen, sulfur, and nitrogen. And for your triple bonds, only carbon and nitrogen, really. Only carbon and nitrogen. So what's this mean? Let's see how we place a double bond using our system. You've already counted your dots. There's more dots than how many valence electrons you're supposed to have. You see your element has either a carbon, and nitrogen, and oxygen, or sulfur. So the first thing in your mind, which is that you should think to yourself, I might want to place a double bond because a double bond can get rid of some of those dots. And that's what we want to try to do is get rid of some of those dots. So look for those elements. There must be, here's another key point, unshared electron pairs too. If you're going to form a double or triple bond, there has to be some pairs of electrons on your structure you drew that are not being used in a bond. We call those unshared electron pairs on the actual elements that are going to have the bond. So the carbon, the nitrogen, the oxygen, and the sulfur. And what we're going to do, and this will be easier when you see it, you're going to remove or erase the unshared pair from that element and from each of the two elements, actually, each of the two elements involved in the double bond. And you're going to add a second shared pair between them to make it a double bond. That sounds complicated. Let's do an example. For example, we know the O2 molecule is a double bond. If you don't, it is. O2 is a double bond. The two oxygens have a total of 12 valence electrons. 2 times 6 is 12. Oxygen has 6 valence electrons, 16th column. There's 2 of them, though, in O2. There's 2 of them right there. So 2 times 6 is 12. If you draw the dot structure like we normally would, you have 14, though. This is how you normally would draw it. Kind of weird because there's not really a central atom, but you have to put those oxygens someplace together because there's only 2 of them. And you got to put 8 around both of them. Well, if you count those dots, there's 14 dots. 14 is higher than 12. So let's investigate whether you can do a double bond. And you can, because oxygen is one of those elements that can do a double bond. So what you do is, and this is the key, kind of gotta watch it, you remove 1 pair of dots from each atom that are not being shared. And they have actually plenty to pick from. So 1 pair from each atom. So maybe you'll see when they disappear, you're gonna take one of these and one of these pairs. And you're gonna take them away. Oh, the computer decided to take that one and that one. So from both involved, this is where our bond has to be. Our double bond's gonna be right there. We take away a shared pair, and then what we do is we add a shared, or take away a lone pair from each, and we add a shared pair. So we really got rid of 2 dots. Whenever you do a double bond, you get rid of 2 dots, which is actually perfect for us because we have 14 dots, but we want to have 12. It has to have 12 valence electrons according to our formula of O2. That is a valid structure because if we count the dots now, there's only 12 dots. 12 dots instead of 14, that's how many we want to have. So that's the structure for oxygen, O2, oxygen gas. And if you look, this one has 8 now because it has 1, 2, 3, 4, 5, 6, 7, 8 because they're sharing these. This one has 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. If 2 unshared electron pairs are replaced with 1 shared pair, like we just did, every atom will have an octet, but there'll be 2 less dots. That's the reason we do this. Double bonds help us with this a lot. Now, if there are still too many dots, the process can be repeated. You can add a double bond someplace else to get rid of 2 more dots. Or maybe you could do a triple bond. Now, triple bonds only work with carbon and nitrogen for the most part, but it can work. So it definitely can work. We'll do an example of that in just a second. Polyatomic ion structures. Great question. What if they give you a polyatomic ion? Can you draw a Lewis dot structure for that? They're covalently bonded. You should be able to. You follow the same exact rules if it has a charge. If your compound has a charge, but you got to look at that charge. If the charge is like a -1, how many more electrons does that thing have? It's got 1 more electron. So you got to add 1 more valence electron to that. And that's what you do. You have 1 more valence electron if you're negatively charged. If you're positively charged, you would remove 1, but we don't see that as often. And then the biggest thing is to tell it's a charged thing, you put brackets around the whole thing. Let me show you an example. Like what if you have a problem that says to draw the Lewis dot structure of sulfite, SO3, which has a -2 charge. Well, you just draw it the same way. Your central atom is S, because there's only 1 of them. There's 3 oxygens. You draw an octet around it, 8 dots. You add oxygens around it. There's only 3 oxygens you can add. You add octets to all those oxygens. You count the dots. There are 26 dots. Trust me, there are 26 dots. Then you count the amount of valence electrons you have in SO3 -2. Well, S has 6, so does oxygen. There's 3 oxygens. So 6 plus 18 plus 2 more. Where did that 2 come from? That 2 right there. -2 means it has 2 extra electrons. Add them up, it has 26 valence electrons. Well, look at this. 26 valence electrons, 26 dots. Perfect. This one's actually a good structure. It's not done yet. What you actually have to do, because it's a polyatomic ion, if you are asked to draw a Lewis dot structure for one of these, you got to put brackets around it and then put the charge outside of it. Just to say, this is not just normal SO3. This is SO3 with a -2 charge. That's how you signify that. So that's all we got for that. I want to do one example, I think, and that's going to require me to move to my iPad real quick. Just do one example of one of these. Let's say, so let me stop presenting here and start presenting over here. So I want to present my screen basically. So I will do that right now. Let's erase all of this.